Hello, this is Jeff Postlewaite, Senior Editor of T&D World with Endeavor Business Media. And welcome to today's T&D World webinar titled Optimizing Transmission Right-of-Way and Environmental Protection, sponsored by Hendrix. So to begin with, let me just let you know how you can participate in today's session. If you have any technical difficulties, just let us know about them in the questions window and our experts will lend you a hand. We recommend disabling any pop-up blockers or Chrome extensions, things like that, that can cause issues with our webinar player. And we want to make sure we get your questions today. So please don't wait for the Q&A session to kick off to send those in. You can do that at any time using the question window, and we will get to those during the Q&A portion to follow the presentation. And please be aware that today's session is going to be recorded and will be available to you on the T&D World website within the next day or so. We'll notify you by email when we're ready. And now I'd like to introduce our speaker for today. Brian Trager is a senior life member of IEEE. He's held various positions in engineering, consulting, and management at American Electric Power Company, Cooper Power Systems, and Fisher-Price. Most recently at Hendrix Wire and Cable, where he works as Director of Technology and International. He has taught electric power engineering at Ohio State University, West Virginia University, and Pennsylvania State. In addition to teaching courses to utility clients, he's also authored over 75 technical papers and articles for IEEE and other national and international organizations in the industry. So welcome to you, Brian.
Great. Thanks for that wonderful introduction, Jeff. So, hello, webinar participants. Thanks for taking the time out of your busy schedule to join us here today. For me personally, it's a pleasure and a privilege to be able to present new ideas, new technology to you. So, super. So, without further ado, we will get right into the slides here, right in the presentation. Right. So we're talking about optimizing transmission right-of-way and environmental protection. So let's see what that's all about. So for an intro, we're going to talk about an intro. I'm going to give you a little bit about HVCC, high voltage covered conductor, what the system objectives are. We'll talk a little bit about the 69 kV spacer cable system and tree wire system. We'll talk a little bit about the 115 kV system. Then we'll get right into what is supposed to be the main gist of this presentation, our right-of-way concerns. How do we expand capacity in existing right-of-way? How do we get a new right-of-way? Why do we need new rights-of-way? Why do we need new transmission lines? So we'll talk about that a bit. We'll talk a little bit about the reliability, the economics. We'll talk about some environmental issues with right-of-ways. And then we'll see if we can settle out on some summary and conclusions. So intro. For those of you who don't know a lot about covered conductor or spacer cable, Hendrix has been around since 1951. We started at 5 kV, went quickly to 15, 25, 35, 46, 69. Now we're up to 115 kV. We're on all 7 continents, over 75 countries. We have a continuous development, continuous improvement, and we're installed for reliability, economics, safety, and as we always say, covered conductor is a design option. It's not to replace bare wire or underground wire or the whole planet. It's just a design option. Use it when it's needed, when it's economical, when it's more safe, reliable. You need to build double circuits, et cetera, et cetera, et cetera. So what is spacer cable? Spacer cable is essentially heavily covered, non-shielded phase conductors held together and supported by a high-strength messenger cable. So you can see the heavily covered phase conductors there. You can see the high-strength messenger on top. That has a couple of functions. It's the mechanical member that holds everything up in the air. It's also your system neutral. It's also your lightning shield, and it's also your protector. It protects from the bundle of conductors from anything that might fall on it from on top. May that be a branch, a tree, a lighting pole, what have you. We've got spacers, they're basically hangers. It's like putting your put those 3 conductors on the spacer, it's like putting your shirt on a hanger and hanging it in the closet. Those phase conductors are under no tension whatsoever. They're just sitting in the spacers and hung on the messenger. Then we got a couple of brackets, tangent bracket, angle bracket, dead end bracket, very simple system. So why do we need the covering? We'll talk a couple of theory slides. When we use a bare wire system, we're basically using air as the insulator. Air is a halfway decent insulator, but you need a whole bunch of it in order to get a sufficient BIL on a 60 hertz withstand. So what we do, and that even though the bare wire system is the cheapest and the easiest, it's still subject to outages due to contact with trees, contact with animals, birds, if you will. So what we do is now we put a little bit of polyethylene insulation on those bare conductors. Now that polyethylene is a really darn good insulator. It replaces that air. So now we're able to bring those phase conductors much closer together, and actually we can have them, 1 inch from each other. That's how good the insulation is. So the poly is going to provide a high impulse strength. It's going to provide a high BIL, 60 hertz withstand, and it's going to withstand short-term either phase-to-phase contact, phase-to-ground contact, phase-to-animal contact without faulting. So we want to make it much more resilient to the environment in which it's installed. The design objectives for that covered conductor is what we want to do is we want to limit the charging current or limit the surface current that's available on the outside of that jacket. So at 15 kV, we said, well, how about we limit it to 1/3 of a milliamp? So if you touch that conductor with your bare hand and you're wearing a copper suit, you're standing in a puddle, it's raining, you have 0 impedance, you're going to get about 1/3 of a milliamp. Now that 1/3 of a milliamp is going to hurt. It's going to give you shock, but it's only 3, 4, 5% of the fibrillation current. So you can certainly let go, and you will let go quickly. And if you're in your right mind, you won't grab it again. So it's not safe, but it's certainly not fatal. So that 1/3 of a milliamp on that jacket is going to allow momentary contact without an outage. And people always say, well, what is momentary? We've got lab tests that say, yeah, we can have that contact for up to a year without an outage. We don't want to have it. We want to keep those phase conductors separate. But if they do touch, even for momentary or extended momentary, we're not going to have damage and we're not going to have an outage. And we say that control the surface charging current is key to virtually everything. We want to prevent tracking. We want to minimize safety issues in case anybody does touch it. We don't want to have an issue. And we want to make sure that we've got that current floating around the outside of that jacket for 40, 50, 60, 70 years. It's not going to degrade the quality of that insulation. We're not going to have PD. So we want to maintain that insulation integrity over the entire useful life of that system. And the conductor insulation system has 3 layers. The first layer is a conductor shield. That's basically going to give us smooth out the electric fields when we're in contact with a ground object. It's going to minimize the partial discharge. It's going to give us a higher BIL, and it's going to give us a longer useful service life. The inner dielectric, you can see it's white there. It's really see-through. It's translucent. It's a very high BIL, high 60 hertz withstand, low density, high molecular weight polyethylene. The other thing that gives us is we use a really soft, low density so that we can facilitate stripping for taps and junctions and transitions, if you will. You put the knife in through the outside layer and it strips off with that soft inner layer. The third layer is what we call the outer jacket. That's where all the tricks are. It's a high density polyethylene. We source the highest high density polyethylene we can because we want abrasion resistance. There is the anticipation that conductor someday is going to touch a tree or rub on a tree or a tree branch. We don't want to have abrasion, so we want very high abrasion resistance. That outer jacket, high-density polyethylene, is also where we put the track-resistant adder. We don't want to have tracking. It's also where we put the UV inhibitor. And that UV inhibitor is a chemical UV inhibitor. It's not fugitive. It will not leak. It puts a chemical umbrella over the molecular chains and protects them from UV rays. And lastly, it's where we put the color. We have black, we have gray, and it depends. There's arguments for black and gray. Usually for the higher sizes and the higher voltages, we use gray because we don't want to have ampacity derating, if you will. And of course, by Ohm's law, if we have higher voltages and we want to keep the current down to 1/3 or maybe 1 milliamp of the higher voltages, we're going to have more insulation. So you can see at 15 kV, the two layers, the A is the semicon, the B and the C are the in and the hour laters. You can see at 15 kV, we have 75 plus 75 mils, 150 mils, which is about 3.6 millimeters. Meanwhile, when we get to 69 and 115, we've got 250 plus 250. We have 500 mils, which is essentially a ½ inch, or about 12.5 millimeters. So that is the insulation thickness. So that's the theory. That's the conductor. Let's talk a little bit about high voltage covered conductor impetus in history. In the 40s and the 50s, New Englanders were kind of tired of outages from storms and trees. They just got fed up. Bill Hendricks invented spacer cable, came in 1951. It was first adopted in the state of Mass, then New Hampshire, then all of New England, the whole U.S., then slowly, Europe, Japan, Scandinavia, Asia, Central Europe, so the whole world. In the late 80s, Electric Power Research Institute asked Hendricks to move from 46, we were only at 46, up to 69 kV. So we had a joint R&D project with Florida Power and Light. We used their labs down in Juneau. And 69 kV spacer cable was developed and introduced in 95 and commercialized. We now have 69 kV all over the place. In 2007, Hendricks was asked by BPA to develop 115 kV high voltage current conductor. So we submitted a joint funding statement to the Department of Energy jointly with the BPA, but we were turned down, luckily turned down, and we decided to go it alone. 2017 to 2024, I'm getting a little bit ahead of myself here, but system design was complete, patents acquired, pilot was installed at Versant, formerly Emera in Maine. In 2019, with PD monitoring every 3 months, we just recently finished Liberty Utilities, their rail trail 2.5 mile 115 kV spacer cable circuit. And we'll take a look at that. That will be energized soon. And in 2024, more stuff, more good stuff coming. So that's exciting. What are our objectives? Why do we want transmission spacer cable? What are the motivating factors? Well, first of all, we want to minimize our right-of-way requirements. We want to have the ability to add circuits in an existing right-of-way. Maybe put a new pole line or multiple circuits on an existing pole line. Maybe we're going to use a voltage upgrade in that same right-of-way. We got a 15, 25, 35 kV right-of-way. Maybe convert that to 69 with a 15 kV below. And the ability to add a circuit without increasing pole height. And we'll see how this goes. Number 3, we want to have reactive voltage support and improved voltage regulation. We know that when we bring the phase conductors closer together, we're canceling out the mutual inductance. We're canceling out 15 to 20% of the impedance, and therefore the voltage at the end of the line is 15 to 20% higher. We've got a better power factor. The cap banks are switching on and off less frequently. The tap changers at the sub are banging around a lot less. So it's got all kinds of benefits there. We'll probably be able to buy less aluminum since we have an improved voltage regulation. So that has a dollar figure attached to it as well. We're going to have improved reliability, ability to withstand momentary contact with trees and animals without faulting. We want to reduce tree trimming. We want to increase the tree trim cycle length. There's a benefit that's not talked about anymore. It was a big deal 20, 30 years ago, reduction of magnetic fields. We'll talk about that a little bit. 80% reduction compared to bare wire, 95% reduction compared to underground. Number 7, we're talking about environmental stewardship. We want to protect the flora and the fauna. How about reducing the carbon footprint? Again, we'll get into this. Close phase spacing can significantly reduce pole heights. There's dollar savings, lower profile, improved aesthetics, all kinds of benefits. And lastly, we're using covered conductor and transmission, essentially where underground or bare overhead is either too costly or implementation is near impossible. So let's, as we go from 15, 25, 35, 46 up to 69, let's talk about it. 69 kV is the same exact system that we're using at 15 kV. Spacers are a little bit bigger. Insulation's a little thicker, but it's the same compact system. We have the same exact covered phase conductors, the same exact messenger, might be a little bigger, the same spacers. They're designed a little bit differently. It's mechanically strong, and it gives us high reliability. That's what it looks like. Our design specs, we'll talk about the spacer in a minute. The cable, again, we've got a close over 960 kV BIL, 218 kV AC breakdown, all kinds of good things with that conductor. So the messenger is the same messenger that we're using at lower voltages. It's AWA, Alumaweld aluminum, or AW, Alumaweld. It has it's the mechanical strength messenger member of the system. Again, it holds everything up. Because we're using Alumaweld or Alumaweld aluminum, it has a high ampacity. It has a low surge impedance, and it also has, because we're using it, and we started using it in coastal areas, industrial areas, it has a very high corrosion resistance. You're not going to rot out a steel core. It's coated. And again, we said before, it's a system neutral ground lightning shield, and it provides protection for the phase conductors above. And it's the same conductor we just discussed moments ago. Now, the one-piece spacer that you saw at the distribution voltages is gone. We can't make a one-piece spacer that's that big. So our first spacer was back when we were still using ring ties back in the last century. It's made of high-density polyethylene, the same dielectric constant as the conductor. It's got a long leakage distance, and we use the same self-washing shed design. 2009, we said, hey, it's time to get rid of that the ring tie and make it ring tie less like our other voltages. We wanted to increase the leakage distance because we wanted to get into areas that were a bit more contaminated. We wanted to put more fins on the horizontal beams, and we wanted to put that good old DM clamp on the messenger. You see the circle around here. And that's going to get us, when you hook that on the messenger, it can't roll backwards or forwards. So now we have more positive staying power of that spacer where it belongs rather than having the ability to move. So that was the second version. Third version just came up 2 years ago. We said, hey, we want to prevent twisting of the spacer close to the poles. We also want to be able to support larger conductor sizes. We're going to be building transmission lines, not with 795 and 954, but at some point, 1192, 1350, 1510. So we want to support larger conductor sizes that are, anticipated for bulk transmission loads. So what we did is we put two arms in the center, were replaced by a single arm with reinforced fiberglass. And that reinforced fiberglass can really, really hold an unbelievable amount of load and compression. We ran the mechanical FEA and tensile tests on the new design. We will do electrical tests at some point, which will apparently be a waste of money, since when you do the BIL and 60 Hertz withstand tests on a spacer, the only thing you're testing is the air. And we have those from the same dimensions, but in any case. And those are the areas of improvement. So you can see that center beam is really massively reinforced. And I'm not going to show you the FEA, the finite element runs, but we increased that by a good 5x, that mechanical strength. So that's wonderful. Okay, so how are we optimizing our right of way? What do we really want to do? Let's go through this piece by piece. We basically want to reduce the profile of the whole transmission line. If you look on the top left, you'll see a bare wire, 69 kV that is constructed in a vertical construction. And you can see from the top of the pole down to the lower phase, we got about 16.5 feet. Right next to it, you have 69 kV spacer cable. And you can see from the top of the pole to the bottom of the bundle, that's 5 feet. So we're essentially saving 5 feet of vertical space. Now, the first job we did at OPPD, we wrote a IEEE paper with the OPPD engineers and discovered that we were reducing the pole heights not by 5 feet, but by 21 feet. That's a heck of a lot of vertical reduction. So the answer is, yeah, it's going to depend on what you are comparing. You got horizontal, you got vertical construction, what kind of poles you're using, where are your insulators, what kind of clearance you need, are you going over railroads, et cetera, et cetera, et cetera. But in this case, we saved 16.5 feet. And if you can see here, we've got 69 kV in a lot of residential areas. This is a Maryland area. You can see the new spacer there on the right. There's an interesting photo. Here's a situation where there's another Maryland Pepco transmission line, 69 kV in a right of way. They had every 6 months they do a helicopter patrol. Helicopter radioed in. You got a tree down on your line. The line's out. They said the line is not out. So they sent people out, trouble men. They took photos, cut the tree down. No problem, no damage to the conductors. If that was a bare wire line, it would be on the ground, and the underbuild would also be on the ground. So that was up there somewhere between 1 day and 6 months, probably somewhere in between that. But that's very comforting from a reliability statistics, reliability index point of view, that we have a tree down on a massive transmission line in a major metropolitan area and no outage. So that's exciting. We've got urban applications. Said OPPD, this was going to a smelter plant. So that was kind of interesting. Here's another urban application, if you will. This is CNEL in Guayaquil, Ecuador. And what they're doing is they're energizing a tram. And this tram, you can see the right side photo, is bringing people in from across the river, thousands of people, so that you're not having those same thousands of people sitting on the highway, coming over the bridge in the morning and jamming everything up. This is brilliant. There was no space for a 69 kV line, but we were able to snake it in here with spacer cable. So this is a nice little application. Here's a Louisiana. There's the city of Natchitoches, triple circuit. We had 132 on the top and 15 kV on the bottom. They framed this up for 69 kV bare wire. The line department said no. I think they said hell no. And they accepted spacer cable. So we got the spacer cable in here. This is a loop that's been around. As soon as we built it, it got hit by Hurricane Katrina. Survived. Had a couple of distorted spacers, but it survived. Never got shut off. And in 2020, it got hit by Hurricane Laura. So we're very, very happy with this, and so is the client. Here's a national park application. This is Parque Villarrica. It's in the south of Chile by the ring of volcanoes. This is a ring around the city of Pucón that goes through the national park. It's a very important national park. They got ski resorts and lakes and all kinds of really cool stuff here. But we basically built a 69 kV line on top and a 25 kV underbuild. And their EPA, which they call CONAMA, Comité Medio Ambiente, basically were with us every day for 6 weeks. They followed us around. They measured everything. We had to have short spans. We had to have short poles. The poles were, I want to say 45 feet. The spans were something like 35 meters. We had to paint the poles a certain green so it fit in with the environment. But very happy. And what I never said is that even though there's a volcano here cut out of the picture, even though that volcano hadn't erupted in 100 years, in 2016 it erupted and blew ash all over the spacer cable systems. And we went out and took a look at it, and it survived very nicely. So we're happy with that. Yeah. And we've got, wetlands. This is National Grid in Massachusetts. This is a double circuit 69 kV ring running around Western Mass, if you will. They had some outages on this, so trees came down on the bare wire, and it was not received favorably by the clientele or the Public Utility Commission. Have a transmission line, you have a distribution line go out, you may have 100, 200 people without lights. You have a 69 kV loop go out, you're in trouble. You've got thousands of people out, and it's really unacceptable. So the conversion begins. This is about 2015. Tropical application. So here is, we've got spacer cable all over the Caribbean and tropical areas around the whole planet. But here's a 69 kV line we built through a national park in the country of St. Lucia, which is in the lower Caribbean at a utility called Lusalec. So very, very happy about this. It's operated real well. We're not really talking about configurations here that much, but give you an idea. This is what a 90 degree corner pole looks like. We snatch off both ends. That's what a horizontal transition looks like. We can have horizontal transitions or vertical transitions. Let me go back here. No, I'll show you that again. So, tree wire. Okay, so up until this time, 5, 6, 7 years ago, we had only built 69 kV and spacer cable. We have a project in Jasper National Park, which is in Alberta, Canada. It's a UNESCO World Heritage Site. It's a very special place for our planet. That city in the middle of that national park is supplied by a diesel gen plant for 45 years. It reached the end of its useful service life. They wanted to change it out and refurbish that diesel plant. Public Utility Commission said, no go, it's not going to happen. You got to connect that Jasper to the Alberta's electricity grid. So this project was met with tons of challenges. I mean, topographical challenges, geological challenges, environmental challenges, and soil. We were unable to directly embed poles. It was rocky, real difficult project. But it was the first 69 kV tree wire installation in North America. So it's a bit of a piece of history here for us. This is what a tangent pole looks like. We're basically using line post insulators with suspension clamps and IPCs to hold those phase conductors. That takes a little bit of explanation. Here's a light angle pole. Here's a heavy angle pole. They put it on an H-frame, but they still had that super, super compact configuration, and a dead end pole. Since we're stripping it, we had to strip it. We had to bring those phases out back to bare wire dimensions. So where are we? 115 kV, the next generation. How exciting. We'll talk about this very similar to the way I talked about the last 69, our objectives, the approach, components, drawings, right-of-way optimization, and some other benefits, power quality improvements, and then we'll take a look at a pilot. Well, the objectives, as you can imagine, are the same exact objectives that we had with 69 kV. We want to improve reliability, power quality. We want to reduce the right-of-way. We want to allow additional circuits to be built in that existing right-of-way. We want to make it easier and faster to get approvals for new right-of-way or right-of-way expansions. Telling the Public Utility Commission you're going to, have a smaller right-of-way and have environmental stewardship, protect the flora and the fauna, and have a smaller carbon footprint is going to get you a quicker right-of-way permit. We want to preserve the environment. We want to minimize public relations issues due to blowing location, routing, design, EMF. We want to help utilities meet the goals for reliability and environmental stewardship as stated in their strategic direction, mission, vision, and regulatory agency targets. And we want to obviously reduce vegetation removal, management, and trimming. So the design approach. Well, as you're probably going to guess, the same exact design approach we have for 5, 15, 25, 35, 46, and 69. We're using the same 69 kV covered conductor for 115. Why? There's a lot of reasons. We don't want to use more material. It's getting heavy. We have more than sufficient 60 hertz withstand and BIL. The charging current on the jacket is acceptable. We don't want to increase the weight and increase the cost. The spacer is massively different, and the pole design specs, you've got to run your calculations and see what kind of pole you need. So again, the spacer is very different. We'll take a look at that. We're going, instead of 30 feet between spacers, now we're going 50 feet between spacers. We say 40 to 70. We're recommending 50. That spacer weight is no longer 2 pounds. A couple of pounds. It's more like 85 pounds. So that's getting heavy. The cable is the same cable we used at 69 kV. So we've been involved with testing this 115 kV system for as much as 15, 20 years. We did initial Corona concept testing on the spacer system, the assembly, the dead end, and the tangent. We did positive and negative impulse testing. We did power frequency dry and wet, flashover testing. We did RIV testing. And again, these are all according to standards, to our standards, since we don't have standards from ICEA or IEEE or ASTM yet. We did spacer, insulator, steep front impulse testing. We did tons of mechanical testing on the spacer, insulator, and the bracket. We did cable BIL, AC breakdown, and wet wood testing. And we did field testing on our pilot circuit every 3 months, probably for the last close to 4 years. So here's the spacer. I didn't even put in the 15 kV spacer. It's about essentially the same size as the 25 kV spacer. We didn't need to put it. You can see when I get to the 69 kV spacer, it's instead of 24 inches high, it's 63 inches high. Instead of 15 inches wide, it's 40 inches wide. When we go to the new 115 kV spacer, yes, it is quite a bit larger, 93 high and essentially 71 wide. So different ball game there at 115 kV. Here's some of the components. Don't want to get too down into the weeds. We're using a galvanized steel support bracket to maintain the separation. We're holding heavier phase conductors, and we're holding there's longer spans between the spacers, so they will be forced to hold more weight. We're using a messenger clamp with a shackle. A Y clevis allow bidirectional movement. We're using polyethylene clamp inserts between the spacer clamp and the cable itself to protect the cable covering, give us a higher BIL. And we're using a high voltage metal cable clamp for mechanical support. So that's what that spacer looks like. So let's talk a little bit about the main issues. How are, we talk about optimizing right of way. What do we want to do? We want to expand capacity. So the issues are we want to either expand capacity in an existing right of way, acquire a new right of way, because we need new transmission lines to carry bulk power. We're getting power back from renewable sites. We've got solar ranches out in the desert. We've got wind farms up on mountain ridges located far from urban loads. We got to get that power back to where it's being consumed. We're also having new things. We're going to have, EPRI's been working on this for years with the IEEE. We're going to have EV charging stations if this electric vehicle thing ever gets out of the barn. We're going to be having EV charging stations. They're going to be on the interstates. They're going to be on 95, on 10, across the nation. So they're going to need some power. And then we've got new load centers for new load growth. I mean, people are moving to Florida, Texas, Arizona. They need a shot in the arm for bulk power. And lastly, climate change concerns. We are not here at Hendricks. We are not climate change alarmists, or that's not our business, climate change. But this is beginning to filter itself into our IEEE, our technical literature. The American Society of Civil Engineers has rated the U.S. electric grid a D+. That's concerning for us electrical engineers. And we have been told, and I guess we could understand this naturally, the climate impacts only intensify threats to an already vulnerable infrastructure. If you've got a transmission tower that's 70 years old and it's getting near to an end of its useful service life and it gets hit by even a weak hurricane, you've probably got a problem on your hands. So these are some of the things we're thinking about. So what are the challenges that we're facing here as an industry? We know that power gen has outpaced transmission line construction. We know that renewable power is expected to grow to 42%. 42% of generation by 2050. Is that correct? I have no idea. That's the expectations. And approximately 1,000 gigawatts of clean energy production remain uncertain due to the lack of transmission infrastructure. We can't even put in these facilities because we don't have transmission facilities to bring it back to load centers. We know, secondly, the new transmission line permits are extremely difficult to attain due to environmental issues, social issues, political issues. It can take a decade, several decades before a permit is granted for a new transmission line construction. The continuous raising of energy consumption has put extreme pressure to utilities to find alternatives on how to increase transmission capacity, not only how to increase it, but increase it in zero time. We know that the legacy transmission lines are old and outdated. Utilities are planning to increase the power output. In many cases, they have size restrictions for their existing right-of-ways. And lastly, we've got inclement weather as pushing transmission line design to be more robust. And when we say more robust, we're talking about weather hardening. We're talking about storm hardening. We're talking about wildfire mitigation. We have to think of all these things now when we're designing new lines and certainly new transmission lines. And if you take a look on the bottom there, let's go to the next slide. Let's say, well, what is a transmission project lifestyle? Well, we got a concept, maybe a feasibility study. We're going to do 3 to 6, maybe 12 months of routing and site survey, identify existing infrastructure. Where are the substations? Where can we build these? What are the routes going to be? We're going to identify environmental and permitting constraints, impact studies, then another 5 to 10 years right away in permitting, negotiating with landowners, easement acquisition, land clearing. That's a lot of work. Design, maybe 3 to 6 months, 9, 12 months of electrical study, line design, structure and foundation design. We know how to do that. Get down to procurement. Hopefully that's going to take 6 months. We put 1 year here. Construction, we put 6 months. Might be 6 months, might be a little bit longer, depending upon how big the line is. Pour foundations, install towers, install conductors, etc. And then commissioning. So that project for new right-of-way can take 7 years if you're lucky, 7 years if you're darn lucky, more like 13 years. But if you got an existing right-of-way, it'll take you 1 to 2 years. So what's the difference between 1 to 2 years building a power line on an existing right-of-way and waiting 7 to 13 years to build it. Well, that difference should be more than intuitively obvious. So how are we going to optimize this right of way? Compact design allows utilities to optimize the existing right of way, resulting in a smaller footprint, decreased reliability. Covered conductor is going to mitigate wildfire risk. We're going to increase the capacity by overbuilds and underbuilds. Substantial savings due to compact footprint. We're going to have carbon footprint reduction and a reduction of EMF fields. This is what it looks like. We'll show you some pictures. So quickly, right of way up. How about if we took a look at, on the left, you've got a horizontal bare wire construction on an H-frame. So that's about 26 foot side to side with 115 kV spacer cable is 8 feet. So we're saving 18 feet on the width of that right of way. Not only are we saving 18 feet, but our 115 kV is taking about as much space as a typical 15 kV line. So we're talking different stuff here. How about vertical height reduction? If I look at the drawing on the left, is a vertical transmission, 115 kV bare, 27.5 feet. We go with spacer cable, it's 40. So now I'm saving 13.5 feet. Do you want to save 13.5 feet vertical height reduction? What is that savings? Are you saving on poles? What else are you saving on? Aesthetics. How about a double circuit? Monopole. Now you're saving 32 feet side to side width on that right of way. That's a heck of a lot of space. How about a double circuit? Double circuit on an H-frame. You don't want to put it on the same pole. You want to put it on 2 poles connected with an H-frame. Now you're saving 26 feet. Spacer cable, 115 kV versus bare wire. Massive, massive savings. Okay, so what are we allowed to say we're saving? We've got to do these calculations for the blowout because my right of way includes the blowout. There's the formulas. Basically, it tells us that we're saving so much on the width, and we're saving 2.25 acres per mile when we're building spacer cable versus bare wire for this case. The 2.25 acres per mile, does that mean anything to you? Does that mean anything to your regulators, to your permitting, to the project, to your trimming? Anyway, I'll leave that to you. Power of quality, reduced voltage drop. We know we got 15 to 20% reduced impedance, 15 to 20% better voltage regulation, buying less aluminum, better end-of-line voltage. Fantastic. We know that because we're canceling out the EMF, we got 76% less EMF compared to bare and 82% less EMF compared to vertical construction. We're playing around a little bit with this carbon footprint thing. So if you do some research here, they say 1 acre of forest effect on greenhouse gases absorbs somewhere between 4.5 and 41 tons of CO2. It also produces 4 tons of oxygen. And this depends on where you are, whether deciduous trees or coniferous trees, the density of the trees. That's why it's a 10-to-1 ratio. So 1 mile of spacer cable is going to absorb between 10 and 92 tons of carbon dioxide and produce 9 tons of oxygen. And if we try to make some conclusions about this, EPA estimates that the average car emits about 5 tons of CO2 a year. So 1 mile of spacer cable carbon footprint reduction would offset 2 to 18, 2 to 20 automobiles. Obviously, our transmission lines aren't 1 mile. So the longer lines, we got more savings. Every ton of carbon dioxide absorbed is significant. And the one thing, you can do all these calculations you want. Green spaces counteract a significant quantity of fossil fuel burning by cars, slowing the rate of CO2 accumulation in the environment. We also have environmental stewardship. We have engineers send us these photos all the time, bald eagles sitting on the line, birds, three-toed sloth in Costa Rica cruising on the line, anteaters, all kinds of stuff. It's really, really impressive, especially when you work in the rainforest and places where we have a lot of animals. Your heart goes out to see them harmed. And again, we're getting back to carbon footprint. If you see on the left, it says for every mile of 100-foot right-of-way through a forest, approximately 12 acres of trees are lost. In the Midwest region, where the average number of trees in an acre is 200, a new 50-mile transmission line would result in the loss of 120,000 trees. So now we're talking numbers. 50 miles, 120,000 trees. That's mind-boggling. Hendrix Basic Cable can save, again, 225 acres and 48,000 trees on a 50-mile line project. Start adding those numbers up. You get carbon footprint reduction. That's going to be very significant. And if you take a look on the right, the construction of a transmission line carries the risk of wildfires caused by conductor clashing, and lines dropping to the ground. We only have to look at the news during wildfire season to understand that this is real. 2022, the U.S. wildfire season saw more than 7.5 million acres of land burned in wildfires. And Hendrix covered conductor effectively eliminates sparks and flashover, thereby significantly reducing the risk of wildfire ignition. Here's the pilot we built in the state of Maine, Versant. It's up by the border with Canada. 5 poles, 4 spans, couple of dead ends, double dead end angle, a light angle, and a tangent. This during construction, we basically use our normal method with a lot of modifications. Our service engineers, our service experts will be on hand when we install a 115 kV line or 69 kV line at your utility. So we'll be able to figure this out before we do it. There's some photos, double dead end transmission. If you look closely, you'll see the arresters there, since you always need a surge arrestor at the intersection of a covered to bare transition, the same as you would put arresters on your riser poles. You see a double dead end. We've got a tangent, and then a final dead end, and that was a vertical dead end. We decided to build it that way. A couple of more photos, I guess. That's the profile on the left. And what we did is, in status update, basically, when we built this pilot with Versant, with EMRA in Maine, we had a company called Exactor come in testing. They did visual inspections and PD monitoring every 3 months, visual inspection of the circuit, checked all connection points of the cable for corona using RF and ultrasonic detectives, and compare them to readings. These Exactor guys know what they're doing with this kind of monitoring. We did a substation inspection, 1-year frequency, examined all poles, cables, spacers, and other hardware. We took some of the stuff down, replaced it. We sent it to the laboratory. We checked for tracking, checked for everything. It's pristine. Very happy with this. So that has gone extremely well. And then we just built our first commercial 115 kV line at Liberty Utilities in the state of New Hampshire. This is in the city of Salem. These are the photos I got from the field folks that just finished this a couple of weeks ago. That's what it looks like. And, this is it. How do you expand capacity in an existing right-of-way? Here they took a 115 kV right away with a 15 kV underbuild and doubled the capacity in the same right of way, if you will. So they've got 2 115 kV lines and 2 15 kV lines. So that's a good story there. Conclusions, basically 69 kV high voltage covered conductors been in successful operation for a long time, since 1995, both basic cable and tree wire. It's mechanically and electrically reliable and proven. We've got 69 kV high voltage covered conductor. We've got it in North America, Canada, South America. We've got it in the Caribbean. Our 115 kV pilot is almost 4 years old, still in operation. Our 115 kV system at Liberty Utilities is going to be energized, if it's not already energized. We've had shown the numerous advantages of high voltage covered conductor systems. They're compact, reliable, safe, reduced right-of-way, environmental protection, reduced carbon footprint, ability to add capacity in existing right-of-way, and environmental stewardship, as well as carbon footprint reduction. And if we could say one conclusion, or one of many conclusions, the march of covered conductor towards higher voltage classes will continue as existing infrastructure declines. New lines are needed for bulk power expansion, connection to renewables, and powering EV charging sites. This will not stop. I mean, we started in 51. We're in 2023 up about 5, 6, 7, 8 voltage levels, and we're going one more as soon as we can. So this is very exciting. I've been very proud to be part of this, and really happy to present this to our industry. And with that, I will return it back to our moderator. Thank you.
Certainly, yes. Interesting stuff there. We had some questions coming in, and you don't need to stop sending in your questions. If you happen to think of one, please keep submitting if you would like. We have one here, pardon me, but these are a little bit short. What is the maximum size of 115 kilovolt Hendrix cable? And they suggest the unit measurement KCMIL. Yeah, that was a question.
Yes. So today, our maximum conductor side would be 954 kc mil AAC. And we will have that problem. We will have that limitation solved in the midterm. So yeah, we're 954 now. We anticipate going up quickly to larger AAC sizes.
Someone was wondering, has the spacer cable experienced a break? And if so, how was it repaired?
Yeah, easy. Phase conductors on spacer cable do not break, because anything that hits them is going to hit the messenger, it's going to break the pole, the spacer cable does not break. However, has it ever broken? Yes. I mean, with 500,000 miles in 72 years, hopefully something is broken. Yes, it has broken. What do? You clean off the ends. You wire brush the aluminum. You clean it off with a solvent. You put the high voltage tape, insulation, and we sell a sleeve, insulated sleeve kit. So we have the instructions for that. And anybody that wants to know a little bit more about that can send me an email or submit that question in email with your return email address, and I will give you complete instructions on tap making, splice making, et cetera, et cetera.
Certainly. This user was wondering, can a standard distribution pole be equipped with spacer cable hardware, or do you have your own standard pole lengths?
Super question. No, I mean, we've used every type of pole on this planet in our working in 75 countries. I've seen every kind of pole there is. You can use a standard pole. The important thing for the pole is that we take a look at it and verify that it can handle the mechanical stress of those phase conductors. But yes, we do a lot of change outs from bare wire to spacer cable, the same pole line with the existing poles.
This question was about dimensions, I believe. How heavy are your 69 kilovolt and 115 kilovolt spacers?
Great. I just showed you that the 115 kV spacer is 85 pounds. The 69 kV spacer is completely high density polyethylene. I don't have the specs in front of me. I would say that's 10 pounds, maybe, because it's only a high density polyethylene. It's pretty light. I mean, I've carried them around on construction projects, and they're bulky but not heavy.
Question from a utility here: can suspension clasps be used on tree wire, or is it?
No, the answer is no. Suspension clamps cannot be used on tree wire. We need to, when I got up to 46 kV, we're still putting the polyethylene conductors on polyethylene insulators. When we get up to 69 and 115 kV, we no longer have those. So what we're doing is we're putting them on line at 69 kV. We're putting them on line post insulators with jackets around the conductor. And I didn't get into explaining that because I was trying to explain concepts rather than components. When we get up to 115 kV, when we do it in a tree wire configuration, we may have a lot of twists and turns. We're no longer putting it on insulators. What we're doing is that we're hanging it from the edge of a line post insulator with a suspension clamp. And at the bottom of that suspension clamp is an insulation piercing conductor with an armor rod. And this is a long explanation for me to give you verbally. You have to need photos of it. But basically, you're using an armor rod to hold that conductor over maybe a 3-foot length. And then you're connecting that armor rod with an insulation piercing connector to the conductor itself. So there is no voltage potential difference across the insulation wall, which might otherwise cause PD or what have you. So we're basically, putting everything at the same potential. But if somebody has more questions about tree wire versus spacer cable at 115 versus 69, send those to me and I will answer them in excruciating detail with pictures, diagrams, and whatnot, and explanations.
A slightly different question about the 69 kilovolt and 115 kilovolt spacer systems. What is their expected service life?
Yeah, this is a tricky question. So when we installed these in 1951, if we went to the original systems that were installed in 1951, I know where they are because I've visited them many times. They're up, around north of Boston. They're still in operation. They're still humming away after 72, 73 years, and they still look great. Maybe we've replaced the spacers. So those systems are cranking away still after 72 years. When we started talking like this, our legal department said, "Hey, you can't say anything has a useful service life for more than 40 years because of some legalese." I forget what it was. So I can say, yeah, it's got at least a 40-year useful service life, but I know for a fact it's good for 40, 50, 60, possibly 70 years useful service life. So the answer is we don't know what the maximum useful service life is, but we know it's 40, 50, 60, 70 years.
Question from a developer here. This may be the last one if time pending here, but they wanted to know what voltage cable a 30 megawatt hydropower plant would need to interconnect to a 138 kilovolt or to a 345 kilovolt line coming from an existing power plant.
Beautiful. Send me that question and I'll give you some calculations and tell you what cable you need. It would be difficult to do that on the top of my head.
Certainly, that's understandable. One more then. What is the span length between poles that are longer for the proposed solution?
Yeah, we're saying now that the 115 kV system, you're looking maybe up to 500-foot spans. These are going to be smaller spans again, but people say, well, I want 1,000-foot span when I'm building a 115 kV transmission line. If you're building 1,000-foot spans, you probably got really tall poles, you got a really clean right of way, and you probably don't need spacer cable. What we're saying is this is not for everywhere. This is where we want to have a low profile. We want to have it going through the trees. We want to have really short poles. We want to have a really short right of way. So those 300, 400, 500-foot spans are relevant in those environmentally important areas. And I'd be willing to argue that point with people who know more about transmission than I do. But that is the philosophy, Jeff.
Sounds good. We did not get to every question exactly, but that is our time. And for those that we didn't have time to get to, we will answer back to you via email. And that is today's presentation for you. On behalf of T&D World, I'd like to thank Brian for his presentation and Hendrix for supporting today's webinar and helping us bring it to you. And thanks to all of you for joining. I hope you have a great rest of your day.
Good. Thank you.